So this is now the lecture for week 15, day 1 on oscillation phenomena. I will first give you an overview of what I mean really with oscillating motion, oscillating behavior, but the word should make this already clear. What is actually much more important to account for different classes now of oscillating behavior. And I want to distinguish here 3 types. One of them is so-called harmonic motion. And harmonic motion is a type of motion where if you formulate second Newton law, the underlying force is proportional to the actual location with which an object experiences a certain force. Once we include friction in that system, then we're talking about damped harmonic motion. And then it very much depends on the strength, the amount of friction, what type of damped harmonic motion we actually encounter. And now imagine if we, in addition to that, disturb independently in a periodic way damped harmonic motion. And let me give you a clear realization for that. Let's imagine you have a mass connected to a spring with no friction. That's what we refer to as harmonic motion. The spring force is directly proportional to the current location of that object. So that what really defines harmonic motion. If now that mass, that block, has friction on the ground, then we're talking about damped harmonic motion. And if we're now connecting that mass to a handle, and that handle is periodically disturbing that mass, the location of that mass, but in a way that it's completely independent of that mass and that spring by itself, then we're talking about a so-called driven harmonic motion. And the periodic behavior of the mass in the spring by itself, as we will see, the respective period or angular velocity is entirely determined by the mass of that object in the spring constant. And if we're now disturbing that system with exactly the same angular velocity, then we come into a phenomena that the amplitude the elongation of that mass will become infinitely large, and this is a so-called resonance phenomena. And you see here a beautiful example for that. Namely, you have a bridge here, and that bridge by itself has a certain oscillating behavior, just like a mass connected to a spring or like a pendulum. And if now the wind perturbs that system, that oscillating system of that spring in exactly the same periodicity, then you can have a very catastrophic effect, a so-called resonance phenomenon. And this in reality actually occurred several times. So let me first define in more detail oscillatory motion. A system in oscillatory motion undergoes a repeating periodic motion about a point of a stable equilibrium. The characteristic example for that is a mass connected to a spring. And now this oscillating behavior is characterized by the frequency, which is 1 over the frequency is a so-called period. So meaning a mass connected to a spring goes through the equilibrium, moves to the left, goes back to the equilibrium, and goes back to the original location. And that time is characterized by the period. And how far the mass moves relative to the equilibrium location, so how much you compress or stretch that spring initially, that is referred to as the amplitude or the maximum accretion from the equilibrium. And so now if you plot here position as a function of time, you see exactly that periodic behavior. So imagine we're compressing the spring by a certain amount, then let go, it goes through 0, through the equilibrium location to the other side, comes back to the equilibrium location, and then the whole motion repeats itself. and that distance from the point where the motion repeats itself, the time scale for that is referred to as a period. You have seen here as a function of form, the function of formed modulo and offset here referred to as a trigonometric function. You could have also a different type of oscillatory behavior where the motion repeats itself, where we're not having just a pure sine or cosine function. So simple harmonic motion now is a very special class of oscillatory behavior where the underlying force is proportional to the current location of the system. And a characteristic example, as I said, is the mass connected to a spring. So how much or how you compress or how much you stretch that spring. And as I will show you, the angular frequency or the period is entirely determined by the spring constant and the mass. Let's look at this equation a little bit more from a mathematical perspective. You have on the left-hand side, we're dealing here with a motion in one dimension, mass times acceleration. Acceleration is the second derivative in time. And then on the right-hand side, we have the respective force, the spring force minus kx, because the restoring force is always towards the equilibrium location. But now, from a mathematical point of view, we want to determine now x of t. But you have here now an equation where x of t appears just as x of t together with its derivative, here the second derivative in time. And a class of equations like this are called differential equations. One thing which will take a little bit of time to sink in, you cannot solve this equation algebraically. There are certain classes of differential equations which can be solved by integration. But some classes of differential equations, you simply have to try a function to see if it works. And I will show you this in a couple of minutes in my handwritten notes. Namely, the trial function x of t equals to a, the amplitude times cosine omega t. If you calculate the second derivative here, x double dot t, you would have minus a omega square cosine omega t. And you can see here, if you insert that second derivative here in the left-hand side here, the cosine omega t term cancels out, and so does a. So the whole part of a cosine omega t cancels out. And what remains then here is m times omega square, and a minus sign equals to minus kx, a minus k. And then you can divide out m, then you have omega square over equals to k over m, then you have exactly that relation. And here's another example now shown for the actual x of t. So imagine we're stretching the spring by a certain amount, namely a here, then let go. That mass moves through the equilibrium location at x equals to 0 to the other side, compresses the spring, comes back to the equilibrium, and then goes back to the original stretch location where x equals to a. And that time scale is referred to as period. So angular frequency can be written as omega equals the square root of k over m. The frequency is omega over 2 pi. So now you can replace your omega. So frequency is 1 over 2 pi and the square root of k over m. And the period is 1 over f, so 2 pi square root of m over k. The phase, there's an additional quantity which I should introduce here, a times cosine omega t plus phi. So phi is nothing else than the characterizing the location of that mass at t equals to 0. So imagine at t equals to 0, x would be a here. Then you put here t equals to 0, so the cosine of 0 is 1, so then in this case phi would be 0 here. But it might very well be that the starting conditions are such that x is different than just a. Then you take into account for that through a different phase here. So let's calculate now since we have x of t, calculate the velocity and then the acceleration. So we know how to do that. Velocity is the rate of change of location, so v is dx dt. This is therefore minus omega a sine omega t. So let's compare here displacement and velocity. In the beginning, when you stretch the spring to a location x equals to a, the velocity is 0. Then the mass goes through the equilibrium. The velocity has a maximum, but pointing in the negative direction. Then the mass comes to rest when the mass is completely compressing the spring. Velocity is 0, and then on the other side, going back through the equilibrium location, but then the velocity pointing in the positive direction, and then going back to the original location where the spring was stretched by a distance a here. Let's calculate now the acceleration. Acceleration is dv dt, which is therefore minus omega square a cosine omega t. And now what you see very nicely here, in the beginning, when you stretch the spring, there's a very large force acting on that. X is equals to a here, giving rise to an acceleration pointing in the negative direction, meaning accelerating that mass towards the equilibrium. When it's in the equilibrium, the acceleration is 0 because x equals to 0. There is no force acting on that, and then the whole process repeats itself, but in the other direction. So please review these graphs: displacement, velocity, acceleration, and make yourself clear about this, using always behind the scene that example of a mass connected to a spring. So another example of harmonic motion could be a simple pendulum under certain approximation. So imagine you have here a connection point to the ceiling. You have a pendulum, a stick here, but the mass of this stick you completely ignore. And then you have a tension in that string or a stick here, and you have the gravitational force of the actual object under consideration here. So now there's a torque, therefore here's the point of rotation. The rotational axis is coming out of the plane. In this particular case, the torque is pointing into the plane here. So R, the location vector calculated torque, is going from the point of rotation to the point where the force is applied, and then cross F. So here the respective force here is under an angle. The torque relative to t is 0 because they are 180 degrees apart. So now you can calculate here I d square theta dt squared. So this is your rotational dynamics equation, moment of inertia times the angular velocity, angular acceleration alpha, equals to the respective torque, which in this case would be the force r cross f, so that the r in magnitude is L, the angle is sine theta here, and then the force in magnitude is mg here. So, and therefore this equals to, we approximate now this for small angles. Then you have here theta, and you see here the change in the angle, the second derivative is directly proportional to theta. And then you can solve this yet again with an ansatz, with a starting function, similar in spirit to something what we have done here before, but now we're not talking about a location x, but an angle theta. Theta of t equals to a cosine omega t. If you were to insert this in here, calculating the second derivative in here, you come to a similar relation, but not among mass and spring constant, but now among g and L here. So the period is 2 pi and the square root of L over g here. And imagine you have now a pendulum on the Earth compared to the Moon, then g would be quite a bit smaller on the Moon compared to the Earth here. You can also reflect that harmonic motion as a uniform circular motion. In this case, the angular frequency of the simple harmonic motion is the same as the angular velocity of the circular motion here. what is behind that is you have the unit circle here. That's the idea to the connection to trigonometric functions. You have here R, a location vector circling around that circle here. Then you have a projection onto the x-axis giving rise to r cosine theta, and on the y-axis giving rise to r sine theta, and then you plot literally that function here. In this case, this would be y as a function of t, y is r sine theta. So for when the angle is 0, y is 0 here, so the location vector would be literally here. So then y is 0. Then that arrow here, also called phasor, is starting to rotate near, now coming to 90 degrees, and then y would be equals to r by itself. So now what about the actual energy, the interplay? Let me go back here to the spring mass system. At one point that mass is clearly, and I can show you this here more clearly at rest here where the velocity is 0, but there are other times where the velocity is very large. On one hand, on the other hand, when the velocity is 0, the elongation, either the stretching or compressing the spring, is in magnitude very large than when the velocity is 0. So there seems to be clearly an interplay between kinetic energy and potential energy stored in the spring. And I wanted to show you this now a little bit more quantitatively and in more detail in the notes, in fact. I'm sorry about this flipping here. So let's see. Let me imagine I will start the starting location here. That line here, that dashed line, indicates the equilibrium location, and you start here, you're stretching the spring, and you're holding that mass in place with a velocity v equals to 0. So the entire mechanical energy is in the spring potential energy, half kx squared. Then you let that mass go, then there's an interplay, the velocity increases in magnitude, the potential energy half kx squared decreases until you come to the equilibrium location where the entire mechanical energy is the kinetic energy and no potential energy. And then the whole process repeats itself until the spring is completely compressed, where you then have only potential energy and no kinetic energy, and so on. And what you see here plotted now is the kinetic energy, which is initially 0. Potential energy is very large, and going like this here, where like a trigonometric function, and k behaving also similar to a trigonometric function. The exact derivation of that I will show you in a couple of minutes, but the beautiful thing is what I will show you quantitatively, if you add potential energy and kinetic energy, you can always come to a constant. Mechanical energy is conserved in the absence of non-conservative forces like friction forces. So these types of harmonic motion where the force is directly proportional to x, like in a spring mass system, plays a very important role to characterize for much more complicated systems the potential energy is a function of displacement. Imagine you have a very complicated looking potential energy curve here, not something like what we would have, for example, in a pure spring mass system. But then you see here this minimum here, this minimum here, and locally around that minimum you can approximate the behavior by the behavior of a spring mass system, the respective potential, namely a half kx squared. X would refer to how much you move away from that minimum here. So this is often very useful to do. So now we're stepping a little bit more towards reality, namely including friction into that system, namely velocity dependent friction. So you have here mass times acceleration equals to the spring force minus b times the velocity, and b characterizes how much type of friction you actually have. And then the type of solution, and then you're getting, if we were to solve this differential equation, which I will not do, which you will learn in a course on oscillation and waves. There's a little bit of math involved in that. would be given like this here. X of t equals to a, the amplitude times e to the power of minus bt over 2m times cosine omega t plus phi. So now you see here x of t plotted here, and it is not surprising the amplitude due to friction dies out after a certain amount of time. Now, it depends very much on how much friction you introduce that system, in addition, given a certain angular velocity of that system characterized by the spring constant k and m. One distinguishes typically three cases here. One which I've just showed you here, case A here, is a so-called underdamped case. So for weak damping, oscillations can still occur and the motion is said to be underdamped. Now, as the damping increases, the oscillation frequency decreases significantly below its underdamped value. And then there's a situation where the amount of damping equals to the angular velocity, and we're talking here about the so-called critically damped case in the case of B. See, you don't have anymore any kind of oscillating behavior. And in case of C, one talks about overdamped case. Now, if in addition to that, I have now a spring mass system, I have friction, velocity dependent friction, and I'm now perturbing that system with in a periodic way, but in a way which is completely independent of that oscillating system of a spring and mass. This is quite complex to solve. You will get a solution of the form x of t times the amplitude cosine omega t plus phi, but the amplitude depends on the frequency. And this is initially not easy to oversee what the behavior will be now on omega naught, which depends on the spring constant k and m, which we have seen before, besides omega d, the driving frequency. So for the moment, let's look at this equation here. Let's imagine we have a case where there is no friction, b equals to 0. Then mathematically what you see here, if you perturb that system where omega d is equals to omega 0, then you divide here something by 0. So therefore the amplitude would be infinitely large. And you reduce that quote-unquote catastrophic effect by including damping in the system. And this is exactly what I show plot here now. The amplitude is a function of the driving frequency. And you see here when the driving frequency equals to the frequency of the simple harmonic motion omega naught, and if you have no damping, b equals to 0, you would have here a pole here. But if you now turn the amount of damping on, increasing that more and more and more from 1/8 omega naught, quarter omega naught, half omega naught, quoted as damping b and dividing this out by tm, then that catastrophic behavior, that very large amplitude is decreased. And I tell you, coming back to this case of the bridge here, this is an important thing in design work. Also for any time you have an oscillating system and there's the potential that there's another driven on oscillation which could perturb in an independent way that oscillating system. So in summary, oscillating motion is a periodic motion that results from a force or torque that tends to restore a system to the point of stable equilibrium. In simple harmonic motion, the restoring force or torque is directly proportional to the displacement. And that displacement could be a distance x, it could be also an angle. We have seen the spring mass systems, one dimension x. In the case of a simple pendulum, it's the angle. In the mass spring system is a paradigm for a simple harmonic oscillator where x of t is a cosine omega t, and omega is then the square root of k over m. In a damped harmonic motion occurs when non-conservative forces act on the oscillating system, and a resonance phenomenon is a high amplitude oscillating response to a system driven by an independent angular velocity, omega d here, but a catastrophic effect can occur when omega d is exactly equals to the angular frequency for simple harmonic motion. So this is all what I want to do to tell you about very basic aspect about oscillations. So let me now come back to the posted notes, which I really would like you to go through. It is a very basic application of second Newton law. So imagine you have our spring mass system here. You have a mass here. This is the unstretched length here. Then you stretch that mass by a certain distance, going from x naught prime to x prime, and I call that difference simply x here. Positive unit vector direction to the right here, free body diagram here, the restoring force Fs is always to the left here, or, well, for positive x, which is here minus k times x times unit vector I here. You insert this in here, applying now second Newton law, equals to m times ax. Then since ax is the second derivative of the location, then what do we find? We find then a differential equation which is minus kx equals to m d square x dt square. You divide out m and you come to an equation. When you want to know now x, well, not only does it involve the actual function itself mathematically, but also its derivative, and that is called a differential equation. So now we have to try literally a function, mathematical function, which could work for that by constraining some quantities in that trial function with quantities which appear in that differential equation. What we will find here now is a characteristic relation between the angular frequency omega here, characterizing the oscillating motion, and quantities characteristic for that system, namely the spring mass system. So if you calculate now the first derivative of that function here, you get minus a omega sine omega t plus phi. That should be really straightforward for you. And then you calculate the second derivative, which is then minus a omega square, sine goes to cosine, omega t plus phi. If you now insert this function, the second derivative in here, and x of t in here, you can immediately see that a cosine omega t plus phi cancel out. And this is what is shown here now. So you insert here on the left hand side minus a omega square cosine omega t. That's what you have here. Plus k over m. So k over m times x, which is a cosine omega t plus phi, which you see here. That is equals to 0. So when can this be 0? Well, you're obviously not having a trivial case where the amplitude is 0 and cosine omega t plus phi for any value in time is 0. So you divide by a cosine omega t plus phi. Then we're left with minus omega square plus k over m equals to 0. And therefore we have omega square equals to k over m, or quoting the period as 2 pi square root of m over k. So this, if you have not seen this before, differential equation, some of you might have seen this very early on in high school, in your last year in a good AP class, where your physics teacher might have pointed out this to you in an oscillating behavior. So this plays an extremely important role in physics or mechanical engineering science, dealing with equations where not only the function by itself appear, but also its derivative. So here's the solution for the pendulum here. The attachment point, there's a little mass here. Using the appropriate coordinates here, cylindrical coordinates, unit vector r points radially outward, theta hat pointing in the direction of the angle, and therefore r theta k using your right hand is coming out of the plane here. So you can calculate then the torque here, which is then minus L mg sine theta times k. So in the opposite direction, as you can see here, relative to that chosen angular direction. Then you set up the dynamical equation, torque equals to I times alpha. The moment of inertia of that point mass here. Moment of inertia is how mass is distributed around the rotational axis, the perpendicular distance squared. So here L squared times m. L squared. And then you insert this back into here, and I leave, you can solve this for yourself, make the approximation sine theta equals to theta, and then you have a similar looking differential equation. Now we're not having x, but we're having theta. So here the second derivative, here not x but theta. But now we no longer have here what we have seen before, namely k over m, characterizing that harmonic system. But now we're having under that approximation for small angles here g and l. And then you can make a similar ansatz, trial function theta of t, theta naught equals to cosine omega t plus phi. And then you get omega square equals to g over L. You have heard me now saying the word Ansatz. Ansatz is actually a German word. I'm so used to saying that because it has been really adopted also in science. Ansatz means simply a trial function. Because in the development of various fields in physics, Germany was dominating the German science area, dominating this field, in particular in quantum theory in the early 20th century. So that's why various German words were simply adopted for that, like that word Ansatz. Anyhow, let me stop here. So let me remind you, go through these slides, listen to that video, can always pause and play. This is hopefully very clear. This is not very complicated, and I want you to simply take very basic aspects as I summarized before away from that. And do me a favor, go through this calculation of the spring mass system in the pendulum, deriving the differential equation, and really determine for yourself the angular velocity for the spring mass system in the pendulum. That would be great. All right, so let's stop here.